In this particular section, we are going to look at graphing of rational functions, whereby we will identify the asymptotes if they exist and the nature of the asymptotes. Now, for graphing of rational functions, we first should be able to identify the asymptotes, and the TI inspired cath actually has a built-in function under fraction tools which is called proper fraction, which actually does polynomial division, and after we perform this polynomial division we can clearly identify the asymptotes. So I'll briefly talk about it when we actually get to that. This table actually summarizes the results that we would be looking for. So a rational function will have two polynomials, and it's the degree of these two polynomials that determine the nature of the asymptote. So if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, the horizontal asymptote would be 0, because in that case the quotient is 0. So it's the quotient that is giving us the nature of the asymptote. So if the two polynomials have the same degree, then the asymptote would be still a horizontal asymptote, but it would be a real number. However, if the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, we would get an oblique asymptote, and if the degree of separation is more, then we would possibly go into a functional asymptote, which could be a quadratic or a cubic. So I suggest that you pause the video over here and analyze this table well. So as a quick summary, it's the quotient that is going to give us the other asymptotes, and is the divisor in the factor form or in the null factor form, which will give you the vertical asymptotes. The other reminder over here is that all the asymptotes need to be expressed in equation form. So the vertical asymptote will be x equals whatever value we obtain, and likewise the other asymptote, which could be a horizontal or a oblique or a quadratic, needs to be in the form y equals whatever the quotient. So let's see how we can use the calculator to determine the asymptotes. So we should be on the calculator page. We go to menu and you'll see number 3 is algebra, and under that you'll see a fraction tool, which is number 9, and then the first of them is a proper fraction. So I'll use the fraction template and go and put our first of the rational functions, which is very straightforward, and when I actually click enter, I will realize that the quotient in this case would be 0, and the calculator obviously is not going to display a 0 quotient. So this clearly tells me that I will have a vertical asymptote, which is x equals 5, and my horizontal asymptote, which is 0, would be y equals 0. However, let's go and make the degree of the numerator the same as that of the denominator. So once again we'll follow the same steps, and let's go proper fraction and enter. So let's get the fraction template, which is 3x minus 1 over x minus 5. Now in this case I will get a quotient, and the quotient is positive 3, which will be my horizontal asymptote. So the horizontal asymptote is y equals 3, and the vertical asymptote is x equals 5. So let's go and consider another case where I'm going to make the degree of the numerator greater than that of the denominator. So let's go x squared this time. Let's say just make it minus 1 over x minus 2, and I get a straight line x plus 2. So y equals x plus 2 is my oblique asymptote, and x equals 2 is my vertical asymptote. So the proper fraction tool is actually a very powerful tool, and it's this section here, of course with the sign, which gives us the other asymptote. Now it could be horizontal, it could be oblique, or it could be a function. So if this was to be a cubic, that I'll do now, let's just copy that, and if I change it to a cubic, you will see I should get a quadratic as my asymptote in this case. And the vertical asymptote is still x equals 2, and that's y equals x squared plus 2x plus 4. That is my other asymptote. Proper fraction is a very powerful tool. So so let's quickly just summarize. When we are doing graphs for rational functions, we need to be able to first of all identify the domain, mark any holes and asymptotes. Now asymptotes ought to be dotted lines and need to be stated as equations, and then obviously to graph we need to know the x-intercept and the y-intercept, and we need to write all the intercepts in the coordinate form. Let's now look at another question. Now this question is something very similar to that was asked in the specialist maths examination a few years ago, whereby you were actually given the equation for the oblique asymptote and the two vertical asymptotes, and they said that the function actually had a dilation by a factor of 4 units. It was the truncus function, and you had to write the rule for the rational function. Now to do this question, actually we will express the function with the common denominator. So instead of using proper fraction, we'll actually have to use the common denominator form, which is also a part of the fractions tool. So let's see how we can do this on our calculator. So to get the common denominator tool, we'll go into menu once again, and then we go to number 3, that's algebra, and then fraction tools, which is number 9, and now right at the bottom you'll see the common denominator, then number 9, and then number 4, and the linear equation that we have is 2x minus 1, which was the oblique asymptote, and then we have got the remainder as 4, which is stated as the dilation factor for the truncus function, and this is a quadratic in the denominator, which is x plus 2 times x minus 3, and this gives me the equation, the rational function. We can actually use a user-defined function. So I'm displaying on the screen how you could create a user-defined function. For you to do this on your CAS, you could actually pause the video and follow the instructions, or you can alternatively download the file from the TI website. This will be available along with this video. So I've got 6 rows which you can see are in the form of a matrix. So to create the user-defined function, you will see that the first of the matrices actually has text information in quotation marks, which basically is telling you what each of those rows is, and the second matrix is the maths behind each of those calculations. So the first row is calculating determining the quotient, etc. So we convert it to the proper fraction form. The second row determines the domain of the rational function. The third is determining the vertical asymptote. The fourth row is determining the quotient, which gives us the other asymptote. The fifth row is giving us the x-intercept, and the last row is giving us the y-intercept. So they are two separate matrices that I have created. So this would be the output I would get if I had this rational function that I've entered over there. And in this case I've stated a domain, but I don't really need to, and this will be the output that you would get. So that's without the domain, that's the output you get. So it's a very powerful user-defined function.